record, I will solve some tasks related to data structures. So the first task is we have to come up with a data structure to the related problems. So the first one, we need to store in a unique user ID. So it means that we should have a unique value. So this size. So duplicates are not allowed. Quick search. Right. So we can use probably sets here because of the uniqueness of the values within a data structure. In the second, the system must process requests in the order they are received. So we should use the principle first in, first out. First in, first out principle. So we should be able to quickly add the element, add to the end, right? So we can use, in this case, we can use a queues. Right, so for storing keys and values, it's necessary to store application settings where each parameter has a name and key and value. So key value principle, key value pairs, right? So the data will be stored in key value pairs. We should be able to quickly access, quick access, or we can say quick search. Right, so duplicates allowed, we can say. Right. So in this case we can use dictionaries because the values are stored in key value pairs and we can access the elements of the dictionaries quickly. The average time complexity for accessing the elements is constant. And also we can store duplicate values, right? So now the company employee hierarchy. So it's necessary to store employee data in the form of a tree. Each employee has subordinates, right? So the format, so the data is stored in hierarchical form, hierarchical form. So each node can have children, or we can say subordinates. Right, so add duplicates. So duplicates allowed. The size can be dynamic. So dynamic. In this case, I think we can use trees. Trees are most appropriate because trees support the hierarchical. They support hierarchical form, and the elements could be represented using the parent-child relationships. So meaning nodes can store the data, and each node can have children. So in this case, we can store it using a trees data structure. So the system processes tasks where priority of a task determines when it will be completed. So we want to be able to quickly add tasks. So the priority of the task determines when it will be completed. So this looks like a queue, but not a normal queue, but priority queue. So the tasks are executed in the order of priority and not in the order they are received. So we can quickly add tasks. Tasks with the average time complexity of being O1 or constant, and execute tasks by priority. Also duplicates are allowed. It's allowed. Dynamic size. So we can use heaps in this case. So priority queues. Right. Managing user friends. So it's necessary to store connections between users in social network. So data is stored as networks. So each node can have several connections, let's say. And so duplicates allowed, and the size is not fixed, so dynamic size. We can use graphs for this task, since graphs allow us to represent the data as networks or in hierarchical form. So graphs could be useful because nodes in the graphs can have multiple different connections, unlike trees. So graphs would be the best choice for this task. Now, ordered list. It's necessary to store a list of numbers in sorted form. So store list of numbers. So it should be sorted in sorted form. Quick access or quick search. So if the list is actually sorted, then it means we can put it in array and access quickly by the indices. So we can access by indices. Let's say by indices, okay. By indices, we can use arrays. For this example, I have a spelling mistake. Indices, right? We can use arrays because arrays, the average time complexity for accessing the elements by indices is constant, and we can store a list of numbers in a sorted form, so with a fixed size, and arrays would be the optimal choice in this case. So now tracking page visits. The system must track unique visits to page on the website and keep track of the total number of visits. So unique elements, let's say unique visits, let's say store unique visits. What else? So to keep the unique visits to the page, to keep the track of unique visits to the page on the website, and keep track of the total number of visits. I think we could use sets here because of the unique visits. So no duplicates. So we could use sets for this problem. User action history. It's necessary to store a list of the user's recent actions so that actions can be undo and redo. So we should be able to store recent actions. Undo, redo. Right. So it means we should have a quick access to our last action. And quick update. Right. Quick access and quick add remove. So add remove the last action. So in this case, I think the most appropriate data structure would be stack, since stacks works with the principle last in first out. So the last action that was executed will be the first that will be removed or added on top of that. So we can use stacks in this case. Right. So the next one, it is required to store names and phone numbers to quickly find a number by name. So looks like we should store the key value pairs. So key value pairs, not unique, most likely. So quick search. And this looks like a dictionary. So we can use dictionaries to implement the key value pairs. A dictionary allows us to quickly search, add and remove elements by the keys, using the key we can quickly search, add and remove elements. So the average time complexity for those operations is constant. So dictionary is the right choice. Finding the shortest route. So we need to design a roadmap where between cities to find the shortest route between two cities. So this looks like we will have some nodes and connections between them. So to store nodes or vertices with edges, right, with connections, quick add and remove, find the shortest road between two cities. Right, so I think we can use graphs. So graphs, they allow us to represent, so the nodes could represent the cities and edges could represent the connections between the cities, and using the nodes and edges we could find the shortest route between two cities. So the next one, checking the correctness of the bracket sequence. So the user enters a string containing brackets. It's necessary to determine whether the brackets are placed correctly. Right, so we will store some string value, store string value, perform operations like add and remove. So quick add and remove operations. So in this case we could use stacks to solve this problem. So stacks will allow us to quickly solve this problem, because the stacks allow us to add and remove with the average time complexity of constant, and stack works with the principle last in first out. So we could use this data structure to so the next, storing frequently accessed objects. It is required to store a fixed number of elements that change frequently with quick access to any of them. So we will store elements with fixed size. Elements with fixed size that could be changed frequently, so we should be able to quick update and quick access to any. Right, so this looks like an array. So we can have a quick access to any elements by the indices and quickly update the elements by the indices, and also we can store the elements with fixed size using arrays. So the average time complexity for updating and accessing the elements by the indices in the array is constant, so we can go with arrays in this case. So the next task is unique words in the text. Given a text, it's necessary to store all the unique words and determine their number. So we should store a string, right, so we store a string, a unique value with a unique value. Wait. Let me change. So so to determine the number of unique words in the text, I think we could use, so duplicates are allowed, I think we could use hash tables. So we'll create an empty hash, and we can pass the text that we should look up within the hash table. So if it finds that the match for the text in the hash table, it will add to the count, so it will print out that the word already exists. If not, it will add it to the hash table. So we can use hash table. Or we could actually use sets as well to store the unique values, since sets, they automatically remove the duplicates and they only store the unique values. So yeah, we would better go off with sets in this case. Duplicates are not allowed. So the number 15, structure of an electronic queue. In a clinic, patients sign up for a queue, and each one must be called in the order in which they were signed up. So the tasks are processed in the order they were received. So duplicates are allowed. The size is not fixed, so dynamic size. I think we could use queues here. So normal queues. We can quickly add to the end of the queue. I quickly add to the end of the queue. So the principle that queues work is that we add. So I mean that the tasks are they are executed in the order they are received. So first in, first out. We can write that down. First in, first out. So the first element that came into the queue, that the element will be executed. So we could use that data structure in the clinic. The next to-do list. It's required to store a list of tasks that can be added to, deleted, and stored by due dates. So we should store a list of tasks. So also should be able to quickly add, delete, and also sort elements. So maybe I think linked list would be a good choice. Linked lists could be a good choice here because linked lists allow us to quickly add and remove elements. So the average time complexity for adding and removing elements from the linked list is constant. Right. Or also we could use a binary search tree as well for sorting the elements. You can write that down. Binary search tree. So the next task is modeling communication between computers. So it's necessary to design a network of computers where each computer can be connected to several others. So again, we should store data as networks. Networks. So each node can be connected to several, let's say, to several nodes, in this case two computers. So the size is dynamic, not fixed, duplicates are allowed. So we could use graphs here. So graphs, they represent nodes and edges that are connected. So the nodes can have different connections, multiple connections, multiple cyclic connections. So it would be reasonable to use graphs in this case. Also, using the graphs, we can quickly add and remove elements by the average time complexity of constant. Right. So the next task is word frequency analysis. So it's necessary to determine how many times each word appears in the text. So quick search, duplicates allowed, dynamic size. Size is not fixed. We could use key value pairs as well. Value. So we can use key value pairs, make the text that we want to look up a key, and to the value of the key we can implement a counter and increase the counter each time that key finds a match in the hash table. So we can use a hash table in this example for this problem, or hash map. So we can use a hash map. Alright, so the next one, rating system. We need to store a list of players with their ratings to quickly find the player with the highest rating. So store a list of players with ratings. Quick search. We should be able to quickly search the player with the highest ranking and with the highest rating. We could use a max heap in this example. So max heaps, they usually store the root of the max heap is usually has the greatest value. So we can quickly access the highest. We can quickly access the player with the highest rating, referring to the first element, referring to the root of the max heap. So the average time complexity for accessing the root of the max heap is constant, but the average time complexity for adding the elements could be log n, but nevertheless we can quickly access the player with the highest rating. So in the next one, checking for duplicates in a data stream. Data is received in a stream and you need to check if the given element has already been received before. So check, we should be able to quickly search, quick search, check for duplicates, right? We could use a hash table for this example. A hash table to quickly search the element and find if we have duplicates or not. Right. So this is it. Thank you for listening.